Good afternoon, everybody. Welcome to the webinar of Taiwan Semiconductor. It is actually now 3 o'clock in the afternoon. Sometimes people, need to dial in, that type of stuff. So we'll give them 1 or 2 more minutes, but I'll tell you a little bit more about the content and the intent. So my name, first and for all, is Jos van Loo. I provide technical support for Taiwan Semiconductor. We published a white paper in the German press, which will be translated in 1 or 2 months also in English and available in English. And we're having a number of webinars around this white paper to explain what the new developments are with rectifiers, especially when it comes to smaller packages. The slides will be available after the presentation, so you will get from your usual contact within Taiwan Semiconductor, you will get the slides which we presented. And on top of that, there will be a Q&A session after the webinar. So you just type in your message in the chat box, and then afterwards we will hopefully answer or be able to answer your questions. Let's go and start and put the agenda on the screen, so the last people that are dialing in now can start following. So we're going to discuss a number of things. We're going to discuss more or less the history of surface mount rectifiers. Then we're going to move on. If you want to go to smaller package, we're going to look at transient thermal impedance. We're going to look at the next issue is going to be the package height. Then we're going to look at thermal resistance, because thermal resistance and transient thermal impedance are 2 important factors when you're going down to smaller packages. We're going to also talk a little bit about process improvements and things we did to actually make rectifiers with 0 defects, which we think is an important improvement on our product line. We're going to also give you an idea of the product cycles and what we think is the future, or what we think will happen. And then we're going to finalize and tell you what the package trends are for surface mount packages and give you a summary. So those are actually the points we'd like to discuss today in the webinar. I think everybody's dialed in now, so we'll start. And we're going to start about the history of surface mount diodes. First and for all, in the 1990s, about 30 years ago, the dominating diode was the MELF. And we started to see transient voltage suppressors first as in what we call SMX packages. We sometimes summarize the name SMA, SMB, and SMC, the 3 most popular packages, surface mount packages on the market at the moment, and we call them SMX just to shorten it. When they were introduced, these SMX packages for transient voltage suppressors, actually they were not designed for rectifiers, and nobody said that their thermal design was good. Actually, it is rather poor from a thermal resistance perspective, and also it has a poor die size to PCB print ratio. So we'll look a little bit more in detail about that. But they were available, and that was the state of the art in 30 years ago. And now slowly the industry is catching up and actually is making some better packages, which we're today going to propose in this webinar, or going to discuss in this webinar. The first thing to say is that flat leads and exposed solder pads are better. When you want to get the heat away from a diode, your flat leads provide shorter traces, and exposed pads have a better thermal resistance junction to case in this case. A number of new packages were introduced recently, so there's been some movement in this industry towards things like slim SMA in the past, but now we've got 4 new packages available in the market. First and for all, I think it's best to visualize what we're trying to tell you. So if you look at, there's no dimensions here, but this is the famous SMA, the workhorse of the rectifier industry. So we're looking at a package which is more than 5 millimeter long, about 2.8 millimeter wide, and the most common die in this package is the S1, and that is usually, some people in China even make it smaller, a 1.25 millimeter die. You can do maximum up to 1.75 millimeter in this package, but the most common one is 1.25 millimeter. As a result, the ratio of that die to the total footprint of the PCB is less than 10%, is around 10%. So that's not particularly very high efficient use of the package. The other thing what you also have to think about, if you go from the die and you follow the lead all the way like this here, you see there's a very long distance between the die where the heat is generated and the PCB. And every millimeter adds thermal resistance. So this package is not really good for getting the heat away from the die. Obviously, the thermal resistance is also determined not just by the lead length, but also by how thick the leads are and how wide the leads are. Now you take the same 1.25 millimeter die and you put it in an SOD 123. This is the same die, the same package, but a different package, obviously. Here you can see this is more optimized to get the heat away from the die. So the distances to the PCB or the solder joint are much shorter, and as a result, you get also a much better thermal resistance overall, the package. What happens in this case is that the die size is the same, but the package size becomes something like 3.8 by 1.9 millimeter. So what you're seeing is that the package size is half of that of an SMA, but the die size is still the same. So you get a 20% or more than 20% ratio now of the die to the footprint, or you get a more than a 50% improvement of the ratio of die to footprint. Before everybody says now we've seen the die and we've seen the slides, and now let's log off because now we understand what the issue is. Actually, there's a little bit more to tell about this die shrinking, or this package shrinking in this case. And so that's what we like to talk about a little bit in the webinar, is what happens if you take a small, the same die and put it in a smaller package. This is really the issue is about transient thermal impedance and thermal resistance. So and that's what we like to discuss a little bit more in detail in the next couple of slides. So first and for all, let's see what those packages look like. We have from small in the top left corner to big in the bottom right corner. We have a number of packages going from micro SMA. And in the bottom slide, or the bottom row, you'll see the workhorses, the SMA, the SMB, and SMC, the older packages. The newer packages are there: micro SMA, SOD 123F, W, sub SMA, and SOD 123HE. And of course, the SOD 128 is also quite a fairly new package. We have also 3 exposed packages now by now: the SMPC and the SOD 123HE and the micro SMA. We'll talk a little about those later on in the about what their advantages are. When is a package actually a power package? Some of these packages are different and from, let's say, small signal packages. A package is actually a power package, capable of handling rectifier currents and power dissipation when the lead is actually soldered to the lead frame. So it needs to be a soldering on the bottom of the die rather than a glue or a die attach adhesive for a small signal. And the top also has to better be a copper clip in most of these packages, or bigger bond wires. Small signal have small bond wires. As such, small signal products cannot handle surges, and the power rectifiers in this case really need solder joints both at the top and the bottom of the die. Now we're going to move to the area of improvements. We're seeing 4 areas: transient thermal impedance and thermal resistance. Those are the subjects we're going to discuss when we analyze in detail what happens if you put a die into a smaller package. The package height, of course, is important, and we're also going to talk a little bit about process improvements that are leading to zero defects. With Taiwan Semiconductor passes automotive audits by tier 1 customers, and we are also proud to be able now to deliver rectifiers with zero defects. First subject, transient thermal impedance. What do we mean by transient thermal impedance? It's a single pulse event. It's a little bit different. A lot of people know transient thermal impedance from, let's say, MOSFETs with the ZTH there and the safe operating area. What we are talking about in the case of rectifiers and transient voltage suppressors is a one-off event. So we either have the typical surges for TVS, like lightning, A20, or ESD in the nanosecond area. And then we have inrush surge current, what happens when you charge a capacitor when it's empty, when you turn on your AC to DC power supply, which is usually 30 or 40 amps, up to a couple of hundred microseconds. So the main difference with the repetitive area is that in this case, the product survives or it fails. What happens is the junction temperature may go briefly over 150 degrees C, but the product actually survives the inrush current and afterwards functions normally. The capability to do so is really dependent on the die size and the quality of the solder joint. When we say the die size and the quality of the solder joint, we mean so for surges up to 1 or 1.5 millisecond. If the surge is less than 1.5 millisecond, the die absorbs all the energy. And the solder joint, of course, also has to be good because otherwise the only part of the die will work. If the surges or if the event become more than 1.5 milliseconds, the package and the lead frames will become important events. So this is actually the key thing to discuss about transient thermal impedance. So only the die for some surges is important. So if we go then, the perfect application for the smaller packages, of course, the TVS diode. Because here we're always talking about a single event. We're talking about a lightning surge or ESD, and all those surges are usually specified by a 10/1000 pulse or 1 millisecond long. The 400 watt then is tested with this pulse length. The die size is the only determining factor. So as a result, if you take the same die into a smaller package, then you get the same performance and you can automatically shrink the package and the PCB footprint. Product miniaturization is straightforward when we are keeping the same die size. In the case of TVS diodes, there is nothing stopping us from going to smaller packages. As a result, you can see here what we're doing. And the best thing to do, understand this slide, is maybe look at the 600 watt line. Let's say 10, 15 years ago, 600 watt was only available in SMB. Now we can put the same die also in SOD 128 and a tin SMA. So this is, the effect of the miniaturization. Then you get, of course, the 400 watt, which is now also available in these packages, which are not only smaller, but also have a lower profile. And that's the second advantage of these smaller packages. Exceptions. There are always exceptions. So we're talking about single pulse events. Actually, sometimes TVS are used as in a repetitive circuit. In a snubber circuit, which protects MOSFETs and is usually a combination of a fast rectifier and a TVS diode, they usually have a duty cycle of, let's say, 2 or 3%, and as a result, they have steady state power dissipation. A low dump is 400 millisecond long, where you really, this DO218 package, which is the package, the large package with this big copper lump at the bottom of it. It looks a bit clumsy for a semiconductor package. Well, that copper is all needed to absorb the energy of a low dump. It's 200 to 400 millisecond long, and the package really needs to help the die here to absorb all the energy. Zeners sometimes are rated at 1 watt, and that's steady state power dissipation. So in that case, you really also need the package and the PCB layout to help the die dissipate the energy. After TVS diodes, the second area where we try to miniaturize is on standard rectifiers. And here the story is a little bit different. TVS, you can rectify 100%. Rectifiers a little bit more complex, but it looks pretty good for standard rectifiers like an S1, that type of product. If you take, let's say, a flyback converter, which is used a lot in LED lamps or chargers of mobile phones, anything under 20 watt or even 50 watt, there's hardly any power dissipation in these bridge rectifiers if they're used as bridge rectifiers. So you're talking, the rectifier typically dissipates less than 100 milliamp, or dissipation in this case would be 100 milliwatt. So the power rating is not that important. The surge current is, though, important. So after that comes a capacitor, and that determines really what type of product you're going to use. The most common ratings here are 30 amp ratings. That's for a smaller power supply of 20 amps, 20 watts, that would be enough. You take the die, the most popular one is the S1M, which is on the second line, and you put it in all kinds of different packages, some bigger, some smaller. You'll see that all these packages can handle this 30 amps, and as a result, the S1 can be downsized, significantly in at least 3 or 4 other packages. So this is the situation with standard rectifiers. It's similar on the S2, and so we have options to really reduce here the size also. What we need to mention here is that in the case of AC to DC applications, the rectifiers are routed on both sides of the PCB. That means that there's always a lot of electromechanical components like magnetics or capacitors, meaning there's always a wave solder side, and the S1s sometimes are put on that side, sometimes put on the top side of the PCB. If they're putting on the bottom side, then really the height difference is really key here, and you really want to get away from that 2.5 millimeters sometimes. If you put it on the top side, you can really use those smaller packages because you don't need the typical 5x5 millimeter solder pads, which we'll talk about a little bit later on. Next thing is package height. So what we'll see here is I already mentioned that the SMD rectifiers are routed on both sides of the PCB, and so you have an existing solder prints of SMA and SMB package on the reflow side of the board. Now this SOD123W can fit on this SMA footprint. The SOD128 can fit on both the SMA and SMB footprints. So here immediately you can actually reduce the component height to 1 or 1.1 millimeter without changing any PCB layouts. It's especially this 1 or 1.1 millimeter that is a demand in a lot of applications, because in a lot of cases the rectifiers are the highest components. If you put them on the bottom side of the PCB, they're usually there with very small chip resistors or capacitors, and so they are the highest components. So there is a big benefit actually in reducing the height and having these new packages. This is demonstrated here, where we take an SOD123 versus the SMA. Where the SOD123W is around 1.2 millimeter. The height difference is not that much, is not that important. The most important is this 1 or 1.1 millimeter magical height limit some designers have. On the next slide, and then we can go to the next subject of thermal resistance, you see the same story here with the SOD128. It can replace an SMA and SMB on the same footprints, so you can immediately have the space savings or the height savings on the bottom of the PCB. What I would like to point out here is that now let's look at some of these solder pads. In our data sheets and in everybody's data sheets, the thermal resistance is usually measured on a 5x5 millimeter solder pad. Now, these pictures here are taken on the recommended solder pads, and which are much smaller. 5x5 millimeter is actually bigger than the package. And as a result, miniaturization is kind of difficult if the solder pads are bigger than the whole package. But here you can tell that on the smaller solder pads, it is possible to still miniaturize. So when are those smaller solder pads acceptable, and when are they not acceptable? The thermal resistance actually consists of 2 parts. It consists of the package-related junction to lead thermal resistance, and then the layout of the user, that is your layout, that is the size of your solder pads, plus also the PCB layout. So those are the 2 parts of the thermal resistance, and usually the part that of the designer is actually much larger than the part of the package. So we took one of the products, which is an SOD123FL, which is the flat lead SOD123. That's because sometimes there's an argument about where does the package thermal resistance stop and where does the user thermal resistance start. If you have these small flat leads, you can easily measure or more easily define the lead temperature and the junction to lead thermal resistance. So in this case, we put this package on a 5x5 millimeter FR4 with 35 micron thick copper pads, solder pads, and we came out with a thermal resistance of 68 Kelvin per watt. The contribution of the solder match pads actually always dominates. So it's about 75%, and that is actually on the 5x5 millimeter. If you put it typically on the recommended solder pads of 1.5 or 2 millimeter square, you actually will increase the thermal resistance by about 10 to 15 Kelvin per watt. That is on the recommended solder pads. So here you can see the dominating factor is the solder pads. So that actually doesn't, go well with miniaturization. So so what we can do here is the following. So not always in rectifiers is there a lot of power dissipation, or standard rectifiers there isn't really. But the one rectifier that usually does have a lot of power dissipation in most applications is a Schottky. Schottky is usually used in an output rectifier, and as a result, it can easily carry 1 or half an amp of current. And so power dissipation of 300, 500, 1 watt is not unusual for a Schottky. If you take a IR camera pictures of PCBs, usually the Schottky is one of the hottest components. You can actually reduce the thermal resistance by having 2-layer or 4-layer PCBs. You can also have thermal vias, or sometimes, but that's expensive, you can do insulated metal substrate as your conducting board. In that case, of course, if you do have a very good thermal resistance, then the miniaturization is easier. The solder pad size is no longer that important, so you can really reduce the overall size of your PCB. And you, of course, in a lot of application, also the exposed pads, which we pointed out to you, they also help reduce the board space in relation to the power dissipation. So that's another area where you can actually critically reduce the size of the PCB. Now we've talked a lot about the advantages of the smaller packages, or when you can use them, related to the height, the transient thermal impedance, and also the thermal resistance. The process improvements on rectifiers and diodes are valid for all packages or all SMD packages, but they're still important to highlight in this case. So we are in a ratio, if you look at Taiwan Semiconductor's own internal data, we're looking at 10 ppb or less than 10 ppb failure rate. Well, what does that mean? We're really looking at 0 defects. That's our main target here, and we think we are close to achieving that. We have a number of things which we are doing to get to that 0 defects. One of them is the part average testing. And that is, if you look at the history of rectifiers, some of them are quite old, and they have, for example, specifications of 5 microamp as their leakage current. Sometimes internally they're tested at 1 microamp, but frankly speaking, the normal distribution stops at a couple of hundred nanoamps. So you could say they're fantastic products because they have a CPK of 20, but they're not really. What happens is you are shipping products outside the normal distribution, which can have a lot of negative effects. So some of these effects are mechanical damage, passivation problems, and contamination issues. So these products would go into the field unless you do PAT testing, which limits the leakage current automatically up to 4 or 6 sigma levels. So those are things we are doing, apart, of course, from qualifying the processes up to AEC Q101 to really get to that 0 defects. Now, there are, of course, a number also of process improvements we're doing, and that tends to be also to the backend, where you can see that we're using matrix lines or vacuum soldering, and we can look at a picture later on of one of the lines. And even in the back end now, we're using a clean room environment. This actually reduces the solder voids a lot, and then that is also a reduction of the ISM, the surge current fluctuations. In the past, there was something called the delta VF test, which tested the VF before and after a short pulse. And that actually gave an indication of the thermal resistance, and actually weeded out the diodes with the worst solder voids. But it wasn't a 100% accurate test, or it's not a 100% accurate test that will lead to 0 defects. What you do need for 0 defects is improvement in the back end and the solder voids to get to your 100% surge rating. Now there's that picture we promised on the back end, and it looks nearly as nice as a front end now. That is also not just an impression; it is actually a clean room environment. When we talk about our improvements, it's important to mention not just this clean room environment, but it's also important to mention that we have the improvement soldering and the improved molding compound or auto molding of the products, which is another error which is eliminated, and there's also no more manual handling or very limited manual handling. If you look at process improvements, we're putting on the back end here. On the front end, we will stay usually with the 4-inch GPP processes. They are very cost efficient, and we can manage them very well. We are also using or going to use in our roadmap a 6-inch planar fab. Planar processes are probably better for potentially in low voltage TVS and Zener applications, in high voltage applications, especially over 1,000 volts, and they are also can be more reliable in making fast, efficient rectifiers, the ones you need with IGBTs, for example, where you have DIDTs of 1,000 ampere microseconds. Their planar processes can also give you advantages in the future. So we're obviously have path testing and AEC-Q 101, but as you can tell, we're also really improving also the processes to come to this zero defects, which we are now claiming to have. The product life cycle of the rectifiers, the 1N4007 it was launched in 1965. The S1 is from the 1980s. So what happens here, as you can tell, that the product life cycles are rather long, and there's very little obsolescence. A lot of the obsolescence in the rectifier industry is actually linked to changes in the front end. For example, MOSFETs going from 0.8 micron to 0.18 micron processes, or analog ICs going from 6-inch to 8-inch wafers. We don't have that. We're on 4-inch GPP, and we will stay that way. So that makes it a little bit easier for us as rectifier manufacturers from the point of view of the front end. Of course, from the back end, there are also changes, but even MELFs or glass diodes are still available. That doesn't mean that you don't have to watch out. In the case of rectifiers, obviously, we are investing only in these new packages. As you could tell from the first two slides, there's less material in these new packages, like in this SOD123W. So that is an advantage long term, which may have an impact on the cost. And so at one stage they will reach cost parity, and we from our side will actually invest only in these new packages, or mainly in these new packages. To summarize here, we see that we have a number of products. Here we see that the SMA definitely is going to SOD123 and SOD123HE. The exposed pads, SMB can be replaced by SOD128 and tin SMA. Each have space savings of close to 50%, and also the SMC is definitely going to go to an SMPC package. There we do both versions. There are two versions on the market, and we have both versions available in our product portfolio. And of course, the DPAC can also be replaced by an SMPC package. And of course, even further miniaturization is possible with the micro SMA, with the exposed pads, to even further reduce certain Schottky applications. So the other thing we need to mention is that the other friend of miniaturization is the Trench-Schottky process. The Trench-Schottky process actually will, for the same die size, have either a better VF, or for the same VF will have a lower leakage current. It will have a slightly higher capacitance, but it will actually help us also reduce die size and get more power out of packages. To summarize, so we are now talking about rectifiers and GPP processes. We are maybe not as fancy or sexy, sometimes we say, as MOSFETs or other high-end power discretes or even power management ICs, but we are now proud that we can also actually deliver them with zero defects. So that is a major step forward also for our company. We have state-of-the-art smaller packages, so we can also deliver them in smaller packages, and we are still making progress also in R&D in these products. So downsizing is an option. You can make them smaller, and you just, when you look at making the design smaller or the layout smaller, you just have to carefully evaluate your transient thermal impedance and your thermal resistance. If you look at those things carefully, you will be able to successfully downsize your existing design. So space savings up to 50% are achievable, and we are actually, of course, these are the future of our lines, and as a result, you should not expect any PCNs or PDNs when using these new package options. And this is also, of course, where all our effort will go to cost reduce and to do our process improvements on these new packages. I think here ends the webinar. I would like to thank you all for your attention. And now, if you have any questions, please enter them in your chat box and just type them to me. And if they are of a general nature, we'll happily answer them. Otherwise, your local salesperson may get in touch with you. While you are typing your questions, let me tell you about the first question this morning. It was about standardization. We had a webinar also this morning. It was about standardization because there's been some problems in the there's been some standardized questions or problems, actually, especially on the SMPC package in the past, about having two versions. I think all the new products are actually done have second sources, are actually quite clearly have second sources, so there is no more confusion in the market about having 5 or 6 different packages available with single sources and that type of stuff. So I think everything can be second sourced. The usual question: can you send the presentation to the attendees, which we'll do. I will confirm that, and I would like to confirm that. Then there's another gentleman that asks here, is the path analysis done for all devices to reach 0 defects? It is done for all AEC-Q devices and also for some other products, and it is done sometimes with 4 or 6 sigma limits. We can discuss that in detail with you if you have questions on it, but the path analysis is done for all devices to reach, or that is an essential part of reaching the 0 defects. I think I'll give you 1 more minute to type in your questions. Usually there's a highlight saying that it says something that you're typing, but nobody is at the moment. So if we reply to all your questions, then I would like to say thank you very much for your attention. Have a lovely afternoon. And oh, there's one more, but it's no. Okay, someone is typing, so I'm going to give that someone actually 30 more seconds to reply to that question. Okay. Okay. Do you have? It's not clear. There's things that will. There's a question about the junction to ambient thermal dissipation about the for the different packages. We will ask your questions actually we will answer your question via email. So I would like to thank you all for your attention and thank you for listening or in your interest in Taiwan Semiconductor. And I wish you all a nice afternoon.